Okay, we're going to start today by talking about the bisection method. Okay, and this method works by letting f be some continuous function on the closed interval ab, with f of a and f of b having opposite signs, which means f of a times f of b is less than 0. Okay, and then we're going to employ the intermediate value theorem. And the intermediate value theorem states that if u is some number between f of a and f of b, then there is a p which is an element of the open interval ab such that f of p equals u. And if u equals 0, then f of a is less than 0 is less than f of b. And so the bisection method uses repeated halving of the interval ab, and at each step you locate the half which contains p. Okay, we can begin by setting a1 equal to a and b1 equal to b. We also let p1 be the midpoint of ab. So that means that P1 equals to A1 plus B1 minus A1 over 2, which is equal to A1 plus B1 divided by 2. Okay? So the entire purpose of the method of bisection is to find the root of the function, and so we're going to list some criteria for the algorithm such that we can find that root. And so we know that if the function of p1 equals 0, then p equals p1, and we are finished. Okay. If f of p1 is not equal to 0, then the f of p1 has the same sign as either f of a1 or f of b1. If f of p1 and f of a1 have the same sign, then p is an element of the open interval AB, and we can set A2 equal to P1 and B2 equal to B1. And finally, if f of P1 and f of A1 have opposite signs, then P is an element of the open interval A1, P1. In this case, we can set A2 equal to A1 and B2 equal to P1. Okay. So next, we're going to reapply the process to the closed interval A2, B2 and continue. Okay, and so in order to demonstrate the bisection method, we're going to go ahead and introduce some example where we need to show that the function of x has a root in the closed interval. And the function we're going to choose is f of x equals x cubed plus 4x squared minus 10 Okay, so in order to see if the bisection method is even applicable, we need to make sure that f of a and f of b are of opposite signs, and we can do that because f of 1, which is a, equals minus 5, and f of 2 equals 14. So we know that f of a and f of b are opposite signs. That checks out. The next step is to take the midpoint of the interval. We know that the midpoint between 1 and 2 is 1.5, and evaluate the function. So f of 1.5 equals 2.375, and that's greater than 0. So therefore the interval for the second iteration will be 1, 1.5. And the reason why is because 2.375 is greater than 0, so our interval will be a, comma, midpoint. And so the next step is to take the midpoint of the new interval, and the midpoint of the new interval is 1.25, and so we're going to evaluate that function. That's equal to approximately minus 1.8. And because that function is negative, the new interval for the third iteration will be 1.25, comma 1.5, with a midpoint of 1.375. And so this process is going to continue on and on and on until you find the root of the function. And in order to perform those iterations, we're going to write a computer code to make that easier, and we'll go ahead and describe that in Microsoft Excel right now. Okay, so now we're going to go ahead and write a computer code to solve the root of a function. And what we need to do is go ahead and start by declaring option explicit, and then we're going to name our subroutine. So we're going to say subroutine, and we're going to say bisect. Okay, and as usual, we want to go ahead and declare our parameters with dim statements, and so we're going to declare our variables. And so when we have this iteration, n is going to be that maximum value of the iteration. And so we're going to call that n. And then I is the indice of the iteration. So we're going to say that I and n are integers. And we're going to say that the interval beginning point is a and the closing point of the interval is b. So we're going to say that the a and b are double precision. Okay, and then we have some other parameters to take into consideration as well, such as the tolerance, the error of the bisection method, and the midpoint. So we're going to say that the tolerance, the error, and the midpoint are also double precision. Okay, and then because this subroutine will require calling a function, we need to call that function something. We're going to say that the function is the root finder, and we're going to say that the root finder is also double precision. Okay, and then we need to name our constant values. And the constant values are the, of course, a, and in this particular a was equal to 1, b was equal to 2, and we're going to choose some tolerance. So the tolerance is the difference between the at what point we're going to stop iterating. We need some value, and so we're going to set the tolerance equal to 0.001. Okay. And the number of iterations, the maximum number of iterations, the more iterations the better in terms of precision, but we're just going to choose 25. Okay. And then we need to go ahead and satisfy the criteria for the bisection method in order for this to even work. And so we need to make sure that the function has different signs at the boundaries of the closed interval b. Okay, if the function doesn't have different signs at the boundaries of the closed interval, then there's no root to be found. Okay, and we can do this with an if-then statement. So if f of a times f of b is less than 0, that means that the function does have different signs at the boundaries, and then we can say then. Okay. So we've gone ahead and encoded that criteria into our subroutine, and then we can say if the function is indeed continuous on the closed interval and has a root to be found, we can implement the bisection method algorithm. Okay. In order to implement the bisection method algorithm, we need to call some function which we declared as root finder. So root finder is going to be the bisection function, which is dependent on several variables. So the bisection function, which we're going to define after the subroutine, is dependent on our left side of the interval A, the right side of the interval B, the tolerance of the numerical method, the maximum number of iterations, n, the midpoint between A and B, m, the ith indice for the iteration I, and the error. Okay, and we're going to go ahead and hard code into this a message box, MSG box. The root of f of x is and then ampersand root finder. So by calling that bisection function, we can display the root of the function in our subroutine. And we can also do something similar for the error. So that error of the function is going to come between the exact value of f of x and the numerical value of f of x. And then we're going to go ahead and say else, and say if the interval f of a if the interval ab does not satisfy the criteria f of a times f of b less than 0, then we're going to have to say that this subroutine is not valid. So okay, so we're going to go ahead and make a message box in that case, which says no use for then we're going to end our if statement, and that's going to be the end of our subroutine. Okay, so that's the end of the subroutine bisect. But because we are calling a function bisection, we have to go ahead and define that function, and we'll do that right now. So we'll say So we'll say function bisection, and then just go ahead and take all of those variables, put them in the function, and we need to declare some new terms. And the new terms that we're going to have to declare are the old midpoint and the new midpoint. So at the beginning, in the closed interval AB, there's a midpoint which is A plus B over 2. Okay, but then as we iterate, that midpoint is going to change. So we're going to have to dim the old midpoint, we'll call M old, and we'll say that's double precision. Okay, and then we're going to declare some criteria. And that criteria is going to tell us whether or not the f of a times the new midpoint is positive or negative. Okay, so we can start the iteration with a do loop and set the old root estimate equal to the present root estimate. So that's just to initialize the do loop. So we're going to initialize the do loop. I'm going to say initialize. Okay. And in order to do that, we're going to say our indice I is equal to 0 to start off with. Do, and then M old is equal to M. So at this point, when you initialize the iteration, the midpoint M is just equal to A plus B over 2. And then we can say that to begin with, we have to estimate what the root is. We have to guess. Okay, and so by guessing, one of the best way to guess it in the bisection method is to just bisect the interval that you're concerning. So M equals A plus B divided by 2. Okay. And this is going to say estimate the root at the beginning. So as a user, you're going to have to guess what that root is initially, and then start your iterations to converge to the actual root. Okay, and what value along the x-axis that evaluating the function will give you f of x equals 0. Okay, then we're going to say I equals I plus 1. So I equals I plus 1 allows that indice to progress in the do loop. Okay. Then we're going to determine the error. If the root estimate is not 0. So in order for it to be a correct root estimate, it has to be equal to 0. So if it's not 0, there's going to be an error. So we can say if the midpoint, and this is the syntax for not equal, if the midpoint is not equal to 0, then the error equals the absolute value of the midpoint minus the old midpoint divided by the midpoint times 100. Okay, and we're going to end that if statement. Okay, and if the root estimate is not 0, the algorithm has to generate a new bracket, because we're going to do this over and over and over again until m equals to 0, or approximately 0. And so we need to determine a new bracket. Okay. And so the criteria is going to be f of a times f of the midpoint. Okay. So if the criteria is less than 0, that means that f of a times f of a times f of m is negative. Then our right-hand point B is going to be our midpoint. Okay. Else, if the criteria is greater than 0, then A is going to be our midpoint. Okay. And then otherwise, if f of a times f of m is 0, there is no error. So once the criteria is 0, it's not going to be greater than or less than 0. It's going to be equal to 0. And in that case, the error will be 0. But we'll have to run it until that's the case. So we're going to end the if statement for the criteria. We're going to end this if statement. And we're going to say that the computation is terminated if the criteria is met, or the maximum number of iterations n are exceeded. Okay. And so what this means is that if the error is less than the criteria, or the indice is greater than the maximum number of iteration, then we can leave our do loop. Okay. So our do loop is going to be closed if these criteria are met. Okay, and if those criteria are met, then the function bisection is equal to whatever m satisfies those criteria. So we're almost done with this. In order for it to be complete, we need to specify a function to be evaluated for a root. Okay. So in this case, our function was f equals x cubed plus 4 times x squared minus 10. That's just some function of x, and of course that can be generalized, but for this specific example, that's what we chose. X cubed plus 4x squared minus 10. And then we're going to end that function. So now we've got our subroutine bisect, we've got the function bisection, and we've got the function f of x. Okay, so we're going to run it, and it says the root of f of x is 1.36523, etc. And the estimated error of f of x is 1 times 10 to the minus 6. Okay,